Increasing global population, climate change and growing urbanization calls for more efficient and sustainable food production. Progress in this sector is needed, and solutions such as controlled environment and automated farming have been shown to be very efficient, as automated plant disease inspection has reduced crop losses by 20 to 40% per year. In particular, there is a need for fully automated phenotyping systems which are able to acquire information from the plants during their growth. These systems would allow the use of modern techniques such as machine learning to make decisions related to the growth environment to maximize yield. Many automated farming systems produced are very specialized, using only one detection system to monitor plants. There is a lack of products which can be used as a shell to accommodate for many different sensors and used for research and testing phenotyping methods. In addition, many existing solutions require high technical background to operate, whilst our solution provides an easy-to-use GUI. The aim of this project has been to increment the abilities of and render fully operational an already existing gantry robot mounted with a multispectral imaging sensor head and present in a greenhouse located in the Fallowfield campus. The project aimed to allow it to automatically phenotype, monitor and act on the growth of plants located in its workspace, by taking images throughout the growth at identical relative locations, by manufacturing a variable spectrum and intensity lighting system, by manufacturing an end effector capable of microdosing, and by programming a GUI to allow for better accessibility. The system is controlled by a GUI, which runs the user interface on the Raspberry Pi, and the Jetson TX2, which runs the software controlling the gantry robot and the sensor head. These two central components communicate with all other subsystems, such as the sensor system, end effector system, and lighting system seen in the diagram. To deliver the desired intensity and spectrum over the plant canopy, a lighting system including 4 luminaires was designed. One luminaire, which includes red, blue, green and far red high-power SMP LEDs selected for optimal plant growth, was manufactured from the designed lighting system. Each channel of the luminaire is controlled separately to achieve variable intensity and spectrum. A custom light sensing system using photodiodes was manufactured so that the light output for each channel of the luminaire can be controlled smoothly using feedback measurements and PI control. Active cooling was implemented using fans to keep the operating temperature of the luminaire at safe levels. The existing gantry was configured to move using 2 selectable predefined motion sequences. The GUI also allows users to program custom sequences. The motion sequences move the head of the gantry between the plants in the workspace. When the gantry reaches a specific plant, a series of multispectral images are captured. The use of multispectral imaging allows for the exploration and utilization of different spectral vegetation indices, which assist in identifying plant health. Once an image is captured, a relevant QR code is extracted to identify and display plant details. The use of image processing techniques which compute the plant biomass center and the LiDAR allow for the system to align itself with the center of the plants and adjust its height accordingly throughout its growth cycle. This allows for consistent plant images to be captured and for changes to be easily noticeable when running the system over months. The system then proceeds to capture a supplementary thermal image using a thermography camera. The images are then later sent to and stored on an online database to allow users to easily view the progress in plant growth. In addition, the system also allows for a user selection interface that shows the areas of water stress, and to allow users to select points and spray them with their relevant nutrients using the constructed end effector. The end effector system for microdosing is made up of an actuator consisting of a linear vertical slider and rotating gimbal, along with a spray system consisting of a DC pump, silicone tubing and spray nozzle. Various components were selected for these two systems and integrated to form a unified end effector. The sprayer is attached to the gimbal and allows the nozzles to be positioned to spray a specific part or leaf of a plant at different angles or sections. This end effector system is controlled through an Arduino Nano, which receives instructions with the locations for spraying from the Raspberry Pi running the GUI. In conclusion, the team was able to achieve all the aims set off at the start of the project, although the integration between all the subsystems in the greenhouse was impeded by access restrictions due to COVID. The team working on the project was based in different locations around the world and had to work remotely throughout a global pandemic. In general, working on a large-scale industrial project gave the chance for the team members to develop many of their soft skills, such as communication, resource management, and organizational skills. Further work on the project would involve construction and testing with plants of the remaining luminaires for the lighting system, implementation of further sensing techniques and spectral vegetation indices, enhancement of the sensor head for reliable daytime imaging, and application of machine learning processing to the collected data.